Okay. Good day. So we're going to start current electricity. We just completed static electricity, and that sort of gave you the background knowledge for understanding current electricity. So one was static electricity. Um, you didn't have flow of electric current. This one is um, uh, in current electricity, you have flow of electric charge. So there's a difference. We're going to start with the concept of electric potential. Um, and in order for you to understand current electricity, you have to understand the concept of electric potential. It is similar to when you have something that has a potential energy. And when something has potential energy, that means it has the potential to convert whatever energy it has into some other form of energy. So it has the potential. Potential energy is defined as, when you have a mass at a certain height above the the ground level. So it has to do with mass and it has to do with height above ground level. So anything that has a height has potential energy because you can convert that potential energy into kinetic energy. In order for you to get something, in order for something to contain potential energy, you have to do some work to give that object a height. You have to lift it, or you have to do some other external work to elevate the object. Say you're gonna put something, if you're gonna put something, high up, okay, you're gonna lift it then, so to speak. But you have to expend energy to lift it up. Okay, so you're giving the object potential energy, whereby you can convert that energy later on into kinetic energy then. Okay, similarly, when we talk about electric potential, we're talking about electric potential energy. And the proper definition for that is potential energy per charge. Okay, and, potential energy, the unit of potential energy or any form of energy is joule, and then the unit of charge is coulomb. So when we talk about electric potential, we talk about joules per coulomb. Okay, so if a charge has electric potential, then it has potential energy. That energy can be converted uh, into another form of energy than our electric potential uh, 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 energy. Okay, so the definition. So we established the definition for electric potential. It's just potential energy per unit charge. Okay, potential energy per unit charge. So we say it's P, potential energy, divided by Q, which is charge. So the metric unit for electric potential is joules per coulomb. So say for instance you lift what I was trying to explain before is that if you lift something off the ground, you have to do work to lift it off the ground. Once you lift it off the ground, it has what we call potential energy. Even though it's not doing anything, the mere fact you lift it off the ground, gravity is going to pull on the object. And if you were to cut the string, the normal thing for this object is to fall to the ground because the Earth's gravitational pull is going to pull it downwards. So it's going to fall. So the potential energy that it gained will be converted to kinetic energy once it starts to fall. Similarly, if we have a charge, if we have a charge and the charge is in an electric field, okay? Once the charge is in an electric field, it's going to have electric potential energy. And the electric potential is the electric potential energy divided by the charge. Okay? So it is the energy possessed by a charged particle due to the location in an electric field. So you always have to think in terms of an electric field. And then, if you put a test charge, say for instance, we have a positive charge object. That positive charge object is gonna have an electric field around it, and we discuss electric fields. Okay, so if you have a positive charge object, that electric field lines are gonna move away from that positive charge object, and because of how we define electric field, so if we have a positive charge object and if we put a positive test charge, so we're always thinking in terms of a positive test charge. If we put a positive test charge in and we have a source charge that is positive, the positive source charge is going to repel that positive test charge. So it's going to push it away. So that is why the electric field lines are going to go away from that positive source charge. So if you have a positive source charge and you put you bring a test charge in that electric field, it's going to push it away. Okay? So the energy possessed by that charged particle is due to the location in the electric field. Remember what we said. The electric field strength is equal to K times Q, which is the charge, divided by the square of the distance of separation. So if you have a positive test charge in a positive, and you have a positive source charge and you bring a positive test charge in that electric field, it's going to push it away. But the amount of energy possessed by the charged particle is going to depend on how close it is to the source charge. Remember, the closer it is to the source charge, the greater going to be the repulsion. So therefore, the energy possessed by the charged particle is going to get greater. The closer you bring it to the positive source charge, the energy it's going to possess is going to be greater. That is why we say electric potential energy is location dependent. The energy possessed by a charged particle is due to the location in the electric field. So just think, we did this in static electricity. Positive source charge and you bring a positive test charge. Once you bring a positive test charge in that field, it's going to repel it. Like charge are going to repel. The closer you bring it, the more the repulsion. Because we know that the electric field strength is equal to K, that constant, times the charge on the source charge divided by the square of the separation distance. So the closer you bring that test charge to the source charge, the greater is the force and the energy. So the potential energy is going to be greater the closer it is to the source charge. So the energy possessed by a charged particle is due to the location. Its location is due to its location in the electric field. Okay? So you have to get that concept because it's important to understand current electricity. So when we talk about electric potential, again, electric potential is equal to the potential energy divided by the charge. Okay? So again, we talk about a positive test charge. If you move a positive test charge from a low potential terminal to a high potential terminal, so all we're talking about, all right, if you have, say you have a positive source charge and you also at one end you have a negative source charge. So you have two charge, and let's draw that so that you get a picture. So if you have a positive source charge right here, and you have a negative source charge, so you have two source charge and a negative source charge right there. So again, the electric field, if you're going to draw the electric field lines, okay, it's going to go this direction, okay? It's going to go away from the positive charge towards the negative charge. So we showed that when we did static electricity. So this is the electric field line, okay? And we also show that the force. So these are going. So these are opposite charge. So this this positive charge is going to attract this negative charge. Okay. So, but if you put a positive source charge now, you bring in a positive test charge. If you bring a positive test charge in the field, so you bring a positive test charge in the field. If you're going to move this positive test charge towards the positive source charge, the natural thing is for it to repel it. You have to provide energy. You have to do work to move this positive test charge towards the positive source charge. Okay? So if once you move this positive test charge towards the positive source charge, you're going to do work. Okay? You have to do work. It is just like you're lifting something off the ground and putting it at some height. So you have to use energy to do that. And say if you bring it to this point, say you bring it closer, so it's going to have more potential energy because you bring it closer to the positive source charge. If you were to release it now, if you release it, the natural tendency would be for the positive test charge to be repelled. So it's going to move from the positive source charge towards a negative charge. Okay? So let's call this position A. All right, let's call this position A. So the position of this positive test charge in this electric field is A. And we can establish another location, say B. Okay, the same test charge, we'll move it closer. If we move it closer, we can call that position B. What I'm saying is that at position B, your positive test charge is going to have more electric potential energy than position A, because you're going to do work. You have to do work because the natural tendency is for your positive source charge to repel your positive test charge, because like charge is going to repel. So in order to bring it to a closer location, you have to do some work. You have to do some work. But once you do that work, you don't have to do anything. It is the natural thing is for at position B is for your positive test charge to be repelled. And once it is repelled, it's going to move towards your negative charge then. Okay? So your electric potential, okay, is greater at position B than position A. So that is why we say electric potential is location dependent. Okay, it is location dependent. So your positive test charge is going to have more electric potential energy at position B than position A. But you have to do work to get it to position B, because it's going to be repelled by this positive source charge. So if you move a positive test charge from a low potential terminal, and the reason why we call this a low potential terminal, because the natural tendency is for this charge to be attracted here. You don't have to do anything. It's normally attracted there. So we call this the low potential terminal. And this is the high potential terminal because you have to do work in order to get your positive test charge over here. It is just like you're lifting an object off the ground and putting it at some height. Okay? If you lift an object off the ground and you put it at some height, it's going to have potential energy, because say you put it on a wall. Once you roll it off the wall, the natural tendency for that object to fall to the ground, because the Earth's gravitational pull is going to pull that object downwards. It's the same thing. If you move your test charge closer to your positive source charge, you're going to give it electric potential energy. So once you release it, it's going to naturally fly in this direction. It's going to move towards your negative or your low potential terminal. Okay? What we're saying is that at the high potential terminal, that's right there, the test charge will move naturally towards the low potential terminal. So from the positive terminal to the negative terminal. So moving a positive test charge towards a positive source charge, you're going to increase its electric potential energy. You're going to increase the electric potential. So, and then once you release it, the natural tendency is for the charge to run in this direction. It's going to move in this direction because it's going to be attracted to this terminal. We call this positive terminal the high potential terminal, and the negative terminal the low potential terminal. High potential terminal because you have to supply external energy. You have to do work to move it towards the positive terminal. Just like you're lifting an object off the ground and putting it at certain height. Okay, once you put it at a certain height, the object is going to have potential energy. And if you roll it off that, say, the wall, that potential energy is now converted to kinetic energy. So similarly, if you move this positive test charge towards your positive source charge, you're going to give it electric potential energy. Okay? And then that electric potential energy will be converted to electric uh, uh, electric uh, energy, right? Okay? All right. So let's move on. I think hopefully you get that concept. All right. So this is what I was trying to draw. Okay, so you have your positive, we call the positive source charge. Call it for positive source charge, we call that the high potential energy. And then this is the negative, is the low potential energy. So if you're going to move your test charge towards your positive source charge, you have to supply energy. You have to do work because the natural tendency is for the positive source charge to repel your test charge. Okay, so you'll have to do external work. But once you get it up here, your test charge is going to now have a high electric potential or high electric potential energy. And then once you release it, it's going to, the natural tendency is for it to be repelled and it's going to be attracted here to the low potential energy. Okay, so that is what we call electric potential. Okay, and similarly, as I was trying to point out, if you can get a car or an object up a hill, you're going to have to do a lot of work to get it up on the hill. Okay, you have to push it, the engine, or the engine gonna have to come into place and you're gonna drive it up the hill. But once it's up here, it has potential energy, and you don't, the engine, you can, if you turn off the engine and the car get to this point, it's gonna roll down because it doesn't require any energy to roll down. That's a natural phenomenon. Okay, the Earth's gravitational pull is going to pull the car downwards. So this potential energy will be converted to kinetic energy. Okay, similarly, if we move our test charge towards a high potential terminal, we don't have to do any work for the test charge to move naturally towards your low potential energy, or sorry, low potential terminal. Okay, all right. So that is electric potential. Electric potential is location dependent. Okay, once it's closer to the source charge, it's going to have more electric potential, more electric potential energy. Now we come to the concept of electric potential difference. So electric potential, as we said before, is location dependent. Okay, if you move a test charge against the electric field from say A to B, then it's going to have greater electric potential at position B. It's going to have greater electric potential energy or electric potential at position B. Work will have to be done by external force in order to get it to B, because the natural tendency again is for the source, a positive source charge, to repel your positive test charge. But you can overcome that repulsion by doing external work. Okay? So if you move your test charge from position A to position B at the I potential terminal, there is a potential difference because this is going to be high potential energy. This is going to be a low potential energy. That is what we call potential, electric potential difference. There's a difference in the electric potential energy. Okay, this electric potential, uh, this is high electric potential, low electric potential. There's a difference because one is high, one is low. Once you have an electric potential difference, then you will have your positive test charge running in this direction, moving in this direction towards your low potential terminal, because that is the natural thing for it to do. It's like pushing the car up on the top of the hill, and once you release the car, you don't have to turn on the engine. It's going to run downhill, because that is the natural thing for it to do. The Earth's gravitational pull is going to pull it downwards. Similarly, if you have an electric field right there, and you have your test charge, positive test charge, and you move your positive test charge to the high potential terminal, that is, you're giving it more potential energy. You don't have to do anything. It will naturally be pushed in this direction, in the direction of the electric field, from the high potential terminal to the low potential terminal. Okay? So that concept of potential difference is important. So when we talk about electric potential difference, it is the potential energy change to a higher value. Okay? So we're moving from a low potential energy to a high potential energy. So it is a potential energy change to a higher value. Okay? Work have to be done. You have to do work to move it from position A to position B. So work have to be done. And when we say when work is done, you have a change in potential energy. So the potential energy here is going to be a certain value. The potential energy at B is going to be a greater value. Okay, it's like you're lifting, or the car is moving up the hill. At certain height, the car is going to have different potential energy. The greater the height, the greater the potential energy. Similarly, right here, the closer it is to the high potential terminal, it's going to have more electric potential. So when we talk about electric potential difference, it is the potential energy change to a higher value from, say, A to B. So work have to be done. So work is done. So the work that is done is equal to the change in potential energy. Change in the potential energy from position A to position B. So the change in the electric potential energy from the two locations. Because again, it's when we talk about electric potential, it's just electric potential energy. It's the same thing. Okay? And the energy, remember we talk about force, the electric force between it's going to be a repulsive force between this positive source charge and the test charge, and the force is equal to K constant times the charge on the source charge divided by the square of the distance of separation. So distance from the source charge is very important. The closer it is the closer the test charge to the source charge, the greater the force. Okay? So you're gonna have to supply work to move it from position A to position B. All right. So electric potential difference is just the difference in electric potential energy from position A to position B. The work that is going to be done in moving it from A to B is equal to the change in the electric potential, or the electric potential energy from position A to position B. So the difference in the electric potential, we call that delta V. Okay? So the electric potential difference, we call that delta V. Okay? And again, as we said, it's equal to the work done. Okay? It is equal to the work done per unit charge. So the difference in the electric potential between the final, this is the final, and the initial location, when work is done upon a charge to change its potential energy, that is what we call the electric potential difference. We denote electric potential difference as delta V. It is the work done in moving your positive test charge from this location to this location. Okay, that is the electric potential difference. It is the difference in the potential, electric potential, from the final location to the initial location. So you're gonna, what you do, you find you find the electric potential at this location, you find the electric potential at this location, and you subtract A from B, okay, and that's the electric potential difference, okay. Because you in order to move from position A to position B, you have to do work, because this positive source charge is going to repel it. You have to do work to bring it closer to the source charge. It is just like you're lifting an object and putting it at certain height. Okay, you have to do work, but once you do the work, you're gonna convert that work into potential energy, and then if you release the object, that potential energy is converted to kinetic energy. Okay, so the difference in electric potential between the final and initial location, this is the final location, initial location. So the difference in electric potential between the final and the initial location when work is done upon a charge to change its potential energy. So the electric potential difference, the electric potential difference is equal to the potential, electric potential at B minus the electric potential at A. That's why it's a potential, electric potential difference. And when we say electric potential, it's electric potential energy, electric potential energy. So that change in electric potential is equal to the work done divided by the unit charge. Is equal to the work done divided by the unit charge. Because remember what we said, in order to move the charge from A to B, you have to do work, because the natural tendency is for this positive source charge to repel your positive test charge. So in order to bring it closer, you have to push it. You have to do work. Work have to be done. So that is why we say the electric potential difference, which is the electric potential difference at a different location, final location, initial location, okay, the electric potential at these two locations, it's equal to the work done divided by the unit charge. Remember that the work is the change in potential energy, because at this location, your charge is going to have a certain potential energy. We call that electric potential. At this location, it's also going to have a certain amount of potential energy. We call that electric potential. So the difference between the two, that's a change in potential energy per unit charge. Now, Alessandro Volta was the physicist who did most of the work in this area. So the electric potential difference, we call that volts. Okay, so we call it volt. So electric potential difference, that is the change in electric potential from B to A, okay, is called the volt, in honor of Alessandro Volta. So a volt is equal to, as I say, it's change in potential energy. Energy is in joules, charges in coulomb. So the metric unit of volt is joules per coulomb. Energy is in joules, charges in coulombs. So that is the metric unit. All right, just going over the same concept again. You have your positive source charge. We call this the high potential terminal, and we call the negative the low potential terminal. It's all because if you're going to move your test charge, say you move your test charge to this location A, you're going to give it a high electric potential. And there's going to be an electric potential difference between this location and this location. So once you release your positive test charge, it's gonna naturally move in this direction from the high potential terminal to the low potential terminal, because it's just like you're lifting an object and you're putting it on a hill and it's rolled down. The natural tendency for that object is to roll off the hill because the Earth's gravitational pull is going to pull it downward. And again, the work is equal to minus q over delta v, where delta v minus delta v is equal to the work done per unit charge. Just rearrange the equation. So you're moving a charge in an electric field requires work or energy input. So you're moving. So again, if you're going to draw your electric field lines, it's going to be from the positive to the negative. If you have a positive test charge and you want to get it towards the positive source charge, you have to overcome that repulsive force. So you have to do work. But once you do the work, your charge is going to have electric potential. So it can move. It's going to have electric potential energy. So at every location, a charge has a position dependent potential. At every point between these your high and your low potential terminal, at every location, your charge is going to have an electric potential. It's going to have potential energy. It's going to be greater. The closer you are to the high potential terminal, greater you are towards the positive side, it's going to have more electric potential or electric potential energy. Okay? The potential difference is simply the difference in potential at the 2 points. So at point A and point B, there's an electric potential difference because you're going to have an electric potential here, which is greater than the electric potential at position B. So there's an electric potential difference, just a difference in the energy at the two locations. But you need that electric potential difference in order for you to get current flowing. All right? So the electric potential difference, as we said, we measure it in volts. The metric unit is volts, and a volt is joule per coulomb. It means that between the two locations, A and B, 1 coulomb of charge will gain 1 joule of potential energy when moved between the two locations. So what we're saying, position A, position B, two locations. 1 volt means that 1 coulomb of charge, if you just have 1 coulomb of charge, it will gain 1 joule of potential energy when you move it from A to B. Okay? So that's what 1 volt means. And we commonly call it voltage. All right? But in order to move your test charge from A to B, you have to do work. And that work is going to be converted into electric potential. And there's going to be an electric potential difference between the two locations. Electric potential difference is what we call the volts. Okay? All right. So electric potential difference, again, work is done on a positive test charge to move it from a negative terminal to a positive terminal. So you're going to have to do work. You have to use energy to push it towards the high potential terminal. Again, we call the positive, we call that a high potential terminal, and the negative we call a low potential terminal. Okay, this work increase the potential energy and hence the electric potential. So you're moving from A to B. You're going to increase the electric. You're going to increase the potential energy, and as a result, you increase the electric potential. Similarly, if you lift an object and you put it, say, on the hill, you're going to increase the potential energy. So same thing, you move the charge from A to B, you're going to increase the electric potential and the electric potential energy. It's the same difference. All right. So when we look at, let's look at this simple circuit. We have, this is a battery, and you see you have a positive terminal and a negative terminal. So this positive terminal in the battery is what we call the high potential terminal, and the negative is what we call the low potential terminal. So all batteries going to have a high potential terminal and a low potential terminal. And then we have wires that connect it to a bulb. So what your battery is going to do, your battery is going to put the positive test charge right here. So it's going to move the positive test charge very close to the high potential terminal. That's what the battery does. It's going to move your positive test charge close to the positive terminal. So once the battery do that, it is natural for that test charge now to be repelled from the positive test charge going all the way to the negative charge. Okay, so what battery does, so when we have a circuit, when you have a circuit, there is what we call an intrinsic circuit and an internal circuit and an external circuit. Your internal circuit is a battery source, and your external circuit is what you usually see. Okay, so your external circuit is going to light your bulb. But the point I want to show is that when you see a positive, it means a high potential terminal, negative is a low potential terminal. So the battery is going to bring the positive test charge to the high potential terminal. So the battery is going to do that. So, and then you don't need the battery because the positive test charge is going to be repelled. So it's going to travel in this direction. And then it's going to light up the bulb, and then it's going to come back to your low potential terminal because your positive test charge is going to be repelled from this, and it's naturally going to travel in this direction. Okay? All right? I hope you can see that. So that is what we were showing right up there. All right? So when you look at your battery, this positive terminal is actually the 1.5 volts. And this terminal right here is actually 0 volts. The potential difference between the two is 1.5 volts. What is your high potential terminal is the 1.5, and the low potential terminal is 0. The potential difference is 1.5. Okay? All right. So when you have a circuit, so all circuits, you're going to have a battery, and then so we call this the intrinsic or the internal circuit, and then you have the external circuit, which they usually tell you to draw. So this is your external circuit with the wires. This is your high potential terminal, your low potential terminal. So when a battery has a rating of say 1.5 volts. The high potential terminal is the 1.5 and the low potential terminal is 0. Okay? And what your battery does, your battery will bring the positive test charge to the high potential terminal. So when it releases it, the charge is going to flow. Okay? The electric so you're going to have a electric potential difference because the high potential terminal is going to have a high voltage. The low potential terminal going to have a 0 voltage. So you're going to have your potential difference. Okay? And the battery provides that potential difference. And then so it's going to have high electric potential right there. Just like the object is on the hill, and once you release it, it's going to flow naturally in the circuit. Okay? So your electric potential will come here, and it's really electric potential energy, and it can convert, it will convert, your electric potential energy is going to be converted to light energy to light up your bulb, and then flow back to the low uh, potential terminal. Okay, so you'll get a loss of electric potential energy in the external circuit. So again, remember what we said. This is your internal circuit. This is your external circuit. You're going to lose electric potential energy once you have to light up your bulb. So the battery is going to give us our high potential and our low potential. The charge is going to flow from the high potential to the low potential. But if there is a bulb in the circuit, it's going to light up the bulb, okay? And it's going to lose some of its electric potential energy. It's going to lose some energy. So the electric potential energy is going to be converted to light energy. So loss of electric potential energy in the external circuit results in a gain in light energy if you have a light bulb, thermal energy if you say have something to heat up, whatever, and then and other forms of non electric energy. So you have your battery source, your which gonna it's your internal circuit. All the internal circuit, all the battery is going to do is to bring the charge to the high potential terminal. And then once you close your circuit, it's natural for the charge to move from your high potential terminal to the low potential terminal. Just as if you have your boulder or something on the top of a hill. Once you release it, you don't have to do anything. It's going to naturally roll off the hill. Okay? But if there's a bulb in the circuit, it's going to light up the bulb. If there's say some other thing, it's going to, you know, if there's a thermal port there for a toaster or something like that, um, it's gonna provide heat. Okay, so you have an internal circuit and an external circuit. So when we talk about a battery, and in circuits you're gonna see battery. A battery is just electrochemical cell or collection of cells. Okay, so a battery is just electrochemical cell or collection of cells, and what the battery does, it supplies the energy to do the work upon the charge. Remember, we said you have to move at this location. Your charge is going to have a certain electric potential. At this location, it's going to have a greater electric potential. The battery is the thing that move it from one location to the next. The battery is the thing that does the external work. So the battery supplies the energy to do the work upon the charge to move it from the negative terminal to the positive terminal. So it's going to move it from the low potential terminal to the high potential terminal. But you need something to do work because you have to overcome this repulsive force. So the battery is going to do that work. It supply the energy to move it from position A to position B, because this is not naturally going to occur. You have to have something that's supplying energy to move it from A to B. That's what your battery does. So the battery is going to supply the energy. It's also going to maintain the electric potential difference across the two ends of the circuit. So the battery maintain the electric potential difference between the two ends of the circuit. So if your battery is rated 1.5 volts, the high potential terminal is going to be 1.5, the low potential terminal is going to be 0. The potential difference is going to be maintained by the battery. But once you close the circuit, then the charge is going to flow naturally. Again, once at the high electric potential terminal, the charge will flow naturally through the wires to the low potential terminal. So all the battery does is supply the energy to move your charge from the low potential terminal to the high potential terminal. So the battery is like you lifting the heavy object on top of a hill. That's what, and you hold it there. Then once you release it, your heavy object is gonna roll down the hill. Okay, so the battery is the thing that supplies that energy to lift it up, move the charge from position A to position B. Okay, the battery is what is the internal circuit. Okay, the external circuit is now the wires through which the charge is gonna uh, flow. So again, if you have a 12 volts battery, 12 volts battery, then if you have a 12 volts battery, 12 volts battery, you're going to have your high potential terminal, your low potential terminal. Your high potential terminal is going to be at 12 volts. The low potential terminal is going to be 0 volts. So the potential difference is 12 volts. So when a battery is rated, say 12 volts, what it means is that the electric potential difference, which is the volts, is 12 volts. Because your high potential terminal is going to be 12 volts, low potential terminal is going to be 0 volts. Okay? So this is your intrinsic circuit. It's going to move your positive test charge to the positive terminal. Once you close the circuit, then your positive test charge is going to be repelled. It's going to be repelled from your positive terminal, and it's going to push it all the way down here. Okay? If in the wires you have a bulb, it's going to light up the bulb. So your electric potential energy will be converted to light energy, some of it. Some of your electric potential energy is going to be converted to light energy. Okay? So again, when you have your battery and it has a 1.5 volts rating, it means that the positive terminal is 1.5 volts and the negative terminal is 0. Okay? So the electric potential difference between the two ends is 1.5 volts. Positive terminal is going to be 1.5 volts. The negative terminal is going to be 0 volts. Okay? The potential difference is 1.5 volts. So the battery just going to supply energy on your test charge. So the external circuits, the external circuit, the charge is moving outside the cell through wires. Okay, so the charge is going to move in wires, and it will, if it encounter a thermal coil, it's going to eat it up. If it encounters any device, it's going to convert that electric potential energy to another form of energy. Whereas your internal circuit, which is the battery, it supplies energy to the charge. So energy is supplied to the charge via the internal circuit, which is the battery. The external circuit is just a series of wires. Okay? So when you look at your external circuit, if you have a positive test charge moving through your external circuit, positive test charge moving through your external circuit, it will encounter a variety of types of circuit elements, such as the light bulb. It's going to light up the light bulb. So your electric potential energy is going to be converted to uh, light energy. It might encounter a motor, and its energy is going to be converted to drive the motor, or eating elements is going to be converted to heat. So your electric potential energy can be converted to multiple different things depending on what circuit element it encounters. Okay? So if you look at this simple circuit, so you have your battery, high potential terminal, low potential terminal. Okay? Your test charge, so your battery is your intrinsic circuit. It's going to bring the positive test charge right here. Once you complete your switch, then it's natural for the test charge to move away. It's going to be repelled from the uh, positive I terminal, and it's going to move all the way here. See the light bulb, some of the electric potential energy is going to be converted to light energy. The bulb is going to light up. The rest is going to flow, and it's going to flow towards the low potential terminal. It's going to flow to the, and then the battery again will have to move the charge from the low potential terminal to the high potential terminal. So the battery will have to do that each time. Okay? So when you draw your circuit, all right, your battery is represented like this. Okay? The longer one is your high potential terminal, the shorter one is your low potential terminal. So your battery is going to supply the energy to bring your positive test charge right here. Once you complete the circuit, then the charge is going to be repelled from your positive terminal, and it's going to flow all the way down and come around. Once it gets to the bulb, it's going to light up the bulb, so that your electric potential energy is going to be converted to light energy, and then it's going to travel back to the low potential energy. And then the battery again is going to move your positive test charge towards the high potential terminal. And then the process starts over and over. So this is your basic circuit, a simple circuit. Okay? Electric potential energy is transformed into other forms of energy, as we have just showed you. So your electric potential energy is transformed into other forms of energy as your charge moves through your external circuit. You'll get a loss of electric potential energy while your charge is passing through the various circuit elements, and that is called a voltage drop. So you're going to get a loss of electric potential energy as your test charge moves through your circuit elements. So you get a voltage drop, and this is what we mean. So you have your battery, okay? Your battery is going to supply the energy to move the charge. You have your high potential terminal, low potential terminal. If it's a 12 volts battery, the high potential terminal, 12 volts, low potential terminal, 0 volts. So the potential difference is 12 volts. So this is your intrinsic circuit. So your extrinsic circuit, your charge is going to move in this direction. Then it's going to light up the bulb, okay? But when you look at your voltage, when the voltage after the bulb is light up is going to be 8 volts. So you have a voltage drop of 4 volts. To light up the bulb, you're going to have a voltage drop of about 4 volts. And we'll have further discussion of voltage drop, but this is the basic concept of voltage drop. To light up your external, to light up your circuit element, you have a voltage drop. The voltage drop by doing that. Okay, so that is the basic concept of current electricity. Uh, we look at some simple circuits. Our next series of lectures, we're going to look at more complex circuits and delve a little bit more into current electricity.